Schön's meteoric rise. In the world of science, some institutions are more than just workplaces, they are legends. Bell Labs, throughout the 20th century, was precisely that, a cathedral of innovation. It was the birthplace of the transistor, the laser, the solar cell, and information theory itself. It was a place where Nobel Prizes weren't just a distant dream, they were a regular occurrence, an expected byproduct of the brilliant minds wandering its halls. So, in the late 1990s, when a young German physicist named Jan Hendrik Schön arrived, he was stepping onto hallowed ground. He was also about to embark on a career so spectacular, so impossibly productive, that it would not only cement his own name in the annals of physics, but also threaten to bring the entire temple of scientific trust crashing down. Schön was, by all accounts, a prodigy. He earned his PhD from the University of Konstanz in Germany, and his early work was promising enough to catch the eye of the titans at Bell Labs. He joined the research group of Bertram Batlogg, a highly respected and influential figure in the field of condensed matter physics. This was the big leagues. Schön's area of focus was the bleeding edge of material science and nanotechnology. He was working on organic semiconductors, materials that promised to combine the cheap, flexible nature of plastics with the powerful electronic properties of silicon. The dream was a new technological revolution. Electronics you could print like a newspaper, displays you could roll up and put in your pocket, and sensors woven directly into your clothes. It was a field brimming with potential, but progress was slow and incremental. That is, until Jan Hendrik Schön put his mind to it. Almost immediately, the breakthroughs began to pour out of his lab at a rate that was simply staggering. While most world-class researchers might hope to publish a single paper in a top-tier journal or in a year, Schön was churning them out at an unbelievable pace. In the year 2001 alone, he was listed as an author on a publication on average once every 8 days. This wasn't just productivity, it was a phenomenon. And the results he was reporting were not minor advancements. They were holy grails of physics, solutions to problems that had stumped the greatest minds for decades. He claimed to have created a transistor from a single organic molecule. This was the ultimate goal of miniaturization, a leap so profound it would make Moore's law look quaint. He reported creating high-temperature superconductors out of plastic-like materials called fullerenes, something previously thought to be impossible. He announced the creation of an organic laser. Each paper was a bombshell, a paradigm shift that sent waves of excitement and disbelief through the global scientific community. The world took notice. Schön was showered with accolades. He received the Braunschweig Prize, the Otto Klung-Weberbank Prize for Physics, and was named one of the top young innovators by MIT's Technology Review. He was on the fast track to a Nobel Prize. It seemed not a matter of if, but when. To understand the sheer scale of his apparent achievement, you have to appreciate the difficulty of the work. Fabricating devices at the molecular scale is an incredibly delicate and complex process. Experiments are finicky, results are often noisy and difficult to reproduce, and progress is measured in tiny, hard-won steps. Yet, Schön's data was always perfect. His graphs were clean, his results were unambiguous, and his conclusions were revolutionary. He seemed to have a golden touch, an intuitive genius for manipulating matter at its most fundamental level. He described his technique using a device called a field effect transistor to coax these exotic materials into behaving in extraordinary ways. By applying a precise electric field, he could induce a whole range of physical phenomenon, superconductivity, insulation, even light emission, all from the same simple setup. It was like he had found a universal remote control for condensed matter physics. His colleagues, including his esteemed mentor Batlogg, were thrilled. They were co-authoring papers that were redefining their field. The pressure at a place like Bell Labs was immense, but Schön didn't just handle it, he thrived in it. He was seen as a quiet, unassuming, and incredibly hard-working researcher who simply had a unique gift. While others struggled, he succeeded. While others produced messy, ambiguous data, his was crystal clear. The scientific world, hungry for the next big thing, eagerly consumed his work. His papers were cited thousands of times. Research groups around the world pivoted their own work to try and build upon his incredible findings. He was not just a rising star. He was the sun around which the entire field of molecular electronics was beginning to orbit. He was writing the textbooks for a new era of technology. But, as the old saying goes, if something seems too good to be true, it probably is. And buried within the beautiful, clean lines of his perfect graphs were the seeds of an unprecedented deception, a fraud so audacious it would be remembered as one of the darkest chapters in the history of modern science. The meteoric rise was breathtaking, but the fall would be catastrophic.
Block 2. Unraveling the fraud. The first sign that something was deeply wrong with Jan Hendrik Schön's revolutionary work wasn't a dramatic accusation or a sudden discovery. It was a quiet, persistent, and deeply frustrating problem that began to bubble up in laboratories from Cornell to Delft to Tokyo. The problem was simple. Nobody could replicate his results. In the world of science, replication is everything. A discovery is not a discovery until it can be independently verified by other researchers. It's the cornerstone of the scientific method, the ultimate defense against error, bias, and outright fabrication. And in lab after lab, physicists who tried to follow Schön's published recipes to build their own molecular transistors or plastic superconductors came up empty-handed. Their devices didn't work. Their results looked nothing like the pristine, perfect data published in. Initially, this wasn't a death knell. Experimental physics is notoriously difficult. Perhaps Schön had a secret technique, a magic touch that he wasn't fully describing in his papers. Maybe their equipment wasn't sensitive enough, or their materials weren't pure enough. For a time, the scientific community gave him the benefit of the doubt. He was, after all, the golden boy from Bell Labs. But as months turned into a year and the number of failed replication attempts piled up, a sense of unease began to creep into the field. The whisper started. How could one researcher working in one lab be so far ahead of everyone else on the planet? The first concrete crack in the facade appeared thanks to the sharp eye of Lydia Sohn, a physicist then at Princeton University. While reviewing one of Schön's papers, she noticed something odd. The paper described an experiment on a single molecule transistor. The data included a graph showing electrical current versus voltage, and like all real-world electronic measurements, it had a certain amount of random, jagged fluctuation known as noise. Later, while reading a paper by Schön, this one on a completely separate experiment involving a different material and conducted at a different temperature, she saw a graph that made her do a double-take. The noise pattern in the data looked hauntingly familiar. On a hunch, she overlaid the two graphs. They were identical. The noise matched perfectly. This was not just suspicious, it was physically impossible. Noise, by its very definition, is random. It's the result of countless unpredictable quantum and thermal fluctuations in a device. Finding two identical noise patterns from two separate experiments is like recording a minute of static from a radio, then recording another minute of static a week later, and finding that the hisses and crackles are exactly the same, down to the microsecond. The odds are not just astronomical, they are zero. It was the ultimate smoking gun. It suggested the data wasn't a measurement of a physical phenomenon at all. It had been copied and pasted. Schön shared her finding with other physicists, including Paul McEwen at Cornell University. Soon, a small group of skeptical scientists began a quiet, informal investigation of their own. They started digging through Schön's massive body of work, and what they found was staggering. The duplicated noise pattern wasn't an isolated incident. They found it again and again. Even more damning, they discovered entire graphs that had been recycled across multiple publications. A figure, supposedly showing the behavior of a silicon-based transistor in one paper, would reappear in another, this time with the labels changed to claim it represented an organic molecular device. It was a pattern of self-plagiarism and data duplication on an industrial scale. The evidence was undeniable, but accusing a star physicist from Bell Labs was a serious career-altering step. McEwen and his colleagues compiled their evidence and, in May 2002, formally alerted Bell Labs. The institution, faced with a potentially catastrophic scandal, had no choice but to launch a formal investigation. They assembled an independent committee of 5 highly respected outside physicists, chaired by Stanford professor Malcolm Beasley. The committee was tasked with one job: to find the truth. They flew to Bell Labs and began their inquiry. They interviewed Schön, his co-authors, and his supervisors. They requested his original lab notebooks and the raw data files from his experiments. This is where Schön's story began to completely fall apart. He claimed he didn't keep detailed lab notebooks, a shocking admission for any experimental scientist. He explained that he had a habit of deleting his raw data files from his computer immediately after plotting them, supposedly to save disk space. This was an excuse so flimsy it was almost insulting. In essence, every single piece of primary evidence that could have proven his experiments were real had been conveniently and systematically destroyed. All of his raw data was gone. The only thing that remained were the final polished graphs, the very graphs that had been proven to be duplicates. The Beasley Committee painstakingly reviewed 24 of Schön's most prominent papers. The conclusion they were moving towards was as clear as it was horrifying. The boy genius of Bell Labs wasn't a genius at all. He was a phantom, building a fantasy world of physics with nothing more than a graphics program and an astonishing amount of audacity.
Scandal. Impact. Legacy. On September 25, 2002, the Beasley Committee released its report, and the findings sent an earthquake through the entire scientific world. The report was a methodical and damning indictment of Jan Hendrik Schön's work. In careful, academic language, it laid out the undeniable truth. Schön had engaged in widespread, deliberate scientific misconduct. The committee found conclusive evidence of fabrication and data manipulation in at least 16 of the 24 papers they investigated. They confirmed the duplicated noise, the recycled graphs, and discovered instances where Schön had simply used mathematical equations to generate data that looked plausible, passing it off as real experimental measurements. The deception was not a one-time lapse in judgment. It was a systematic pattern of fraud that spanned years and dozens of high-profile publications. The fallout was immediate and brutal. Bell Labs, once the proud home of its star physicist, fired Schön on the very day the report was released. It was a swift and necessary amputation to save the institution's credibility. What followed was an unprecedented academic purge. The world's most prestigious scientific journals were forced into the humiliating position of retracting paper after paper that they had once championed on their covers. In total, more than 24 papers bearing Schön's name were withdrawn, one of the largest mass retractions in the history of science. His celebrated awards were rescinded. The University of Constance, his alma mater, initiated proceedings and ultimately revoked his doctoral degree, declaring it had been obtained by fraudulent means. In the span of a few months, Jan Hendrik Schön went from being a candidate for the Nobel Prize to a pariah, his name becoming a permanent synonym for scientific fraud. The collateral damage was immense. His co-authors, particularly his supervisor Bertram Batlogg, had their reputations severely damaged. The Beasley report cleared them of any complicity in the fraud, concluding that they had been deceived along with everyone else. But in the court of scientific opinion, questions lingered. How could they have co-authored so many papers without ever seeing the raw data? How could they not have noticed the impossibly perfect results? The scandal served as a harsh lesson in the vulnerability of collaboration and trust. A single dishonest actor could tarnish the careers of an entire team of well-respected scientists. Beyond the individuals involved, the Schön scandal triggered a profound crisis of confidence in the scientific process itself. The peer review system, the gatekeeping mechanism designed to filter out bad science, had failed spectacularly. Dozens of expert reviewers had looked at Schön's manuscripts and, seduced by the groundbreaking claims and clean data, had given them their stamp of approval. The scandal forced a painful period of introspection. Journals began to implement much stricter policies regarding data. Now, authors are often required to make their raw data available upon request, and some journals demand it be submitted alongside the manuscript. The case highlighted that peer review cannot be a system based on blind trust. It must be one of skeptical verification. So why did he do it? What could possibly motivate a brilliant young scientist to construct such an elaborate and ultimately doomed house of cards? Schön himself has remained largely silent, but most observers point to a toxic cocktail of immense ambition and the crushing pressure of modern publish or perish academia. Schön wasn't just trying to succeed, he was trying to be a legend. He saw what the scientific community wanted: clean results, revolutionary breakthroughs, and he simply decided to manufacture them. Perhaps he started with a small fudge, a minor manipulation to make a messy graph look cleaner, and found that it was rewarded. And so the lies grew, becoming more and more audacious until his entire career was built on a foundation of fiction. Today, the legacy of Jan Hendrik Schön is a cautionary one. His story is taught in scientific ethics courses around the globe as a definitive case study in research misconduct. While the scandal was a black eye for physics, it also, in a strange way, demonstrated the ultimate strength of the scientific method. His fraud was not uncovered by an administrator or a journalist, but by other scientists doing what they are supposed to do: questioning, testing, and demanding evidence. Science is not a collection of infallible truths handed down by geniuses. It is a messy, human process of self-correction. Schön's epic fraud revealed a critical vulnerability in the system, but the system, in the end, corrected itself. It proved that truth in science will eventually surface, no matter how deeply it's buried under a mountain of lies.